in the context of Petri nets. So please.
Thank you very much for the kind introduction, and double thanks for the kind invitation and the opportunity to talk here. In fact, it will be a question of physics, but I am not a physicist, and I'm afraid I might disappoint you, but we will see about that later. The idea of this talk is to show you why it is that many researchers, including myself, love to work with Petri nets, and the particular aspect of concurrency that can be expressed in them. And the main thesis that I try to convince you of is that this model and this phenomenon are still fertile today and transcend the boundaries of scientific disciplines. So I will start with an informal introduction to how Petri nets work, famous token game. Then, following Carl and Petri to a tiny little extent, I will actually talk about some connections with physics, and then show some applications in engineering contexts, in particular in the context of telecommunication networks, and in the last part, the relatively recent impact that the model has started to have in biology. So we're coming to life sciences. So when he usually goes back when discussing about Petri nets to the doctoral thesis of Carl and Petri, deceased 4 years ago, that was submitted in 1961 and defended in 1962, which actually talks about communication with automata. So the real issue here was not so much defending the net model that was in his mind well before that, but really to see how entities interact and how the entities interacting span physical processes and how you can understand these. If you haven't seen a Petri net, well, it is not much of a secret. Like I said in the announcement, we draw some cycles and boxes or bars and some arrows between them, and you put some little objects inside the places that you're done. Then what is interesting is how do you interpret these? Well, the circles are places, positions in which objects can exist or where conditions can hold. Transitions are the boxes. They represent actions that are possible, events that can occur, depending on the availability of resources. And finally, the arrows show where tokens are consumed, where tokens are produced. So right here, we are in a situation where this transition here is enabled because it has enough tokens in the incoming places, and it will produce output on this place here. In this model, it will be the last time in this talk, I used non-one weights on the arcs for simplicity. Later on, all weights on the arcs will simply be one. So right here we consumed two tokens from the upper place and only one from the lower, because this is all the arcs asked of us. And on P2 we have two new tokens created. So this is the basic step of the token game of Petri nets. And of course, these graphs are much bigger than that, and actions follow one another and enter in relation with one another. And this is what net theory is all about. As I said, the topic of the talk is different connections, the different fields of applications that you can have with Petri nets. They're not just mathematical objects. It has been said that drawings like this probably popped up during the adolescence of Adam Petri when he was learning chemistry at school. He is said to have drawn images like this to understand chains of reaction. So here you have carbon oxide and a chain of other substances that enter in a complex reaction. And at each step, the reaction is a transition, and the substances are represented by places of their presence and absence by tokens. So nature has played a role behind the idea of nets from the very beginning, and you can go a lot further than this. These are pictures presented at the Petri conference in China 2008 by Rüdiger Falk, worked with Petri on this. The interest in using Petri nets as models is in the fact that you have a strict locality of interactions. A state is important locally, and action acts locally on its immediate physical surroundings. So, as we'll see later, you can you retrieve a phenomenon that physicists know in relativistic circumstances, or basically everywhere when they account for huge speeds. So if you know these diagrams by Hamann-Minkowski from the beginning of the century, then you know that these cones can be seen as those parts of the space in which any trajectory of an object must lie. So you can move from bottom to top inside the red or the blue or the green cone, but you cannot jump from A to C directly because this would be a spatial step that would be much too fast to make for any physical object. And so at these points A, B, and C, you have different clocks in each site that are not directly synchronized with one another. So in a sense, there is no global time, there is no global clock. As said, physicists have developed quite a number of techniques for this. And what might surprise you here is that, well, Minkowski geometry and so forth is typically real geometry, continuous, and Petri nets are inherently discrete objects, they are graphs. Well, this is precisely a dichotomy that Petri has always denied. His view is that you have a model that is continuous, even with the finitary means of Petri nets. So, just for an illustration, a grid proposed by Petri, composed of transitions and places as usual, can be used as a model for space-time, and you can retrieve the equivalent of Minkowski cones in them. Well, what is unfortunate, of course, is that time moves up here and down on the right-hand side, but the principal idea is the same. Any signal can have impact only along the lines of the Petri net, along the arcs. And if you go horizontally, go with quotation marks, then you move in space, whereas orthogonal to that you have the progress of time, And what he proposes is to use, instead of these coordinates that are foreign to the system, to work with coordinates that are intrinsic, in the sense that you have diagonal lines from left to right that you can use as an x-axis, and the others as a y-axis, and they mark the extremes of physical connection that are possible. What is interesting here is that you can identify many things in the geometry of this regular grid. In fact, what Petri proposes here is to see the grid as an unfolding of regular tiny structures of this shape, and conversely to see sections of the grid as representations of small Lorentz transformations in the space-time geometry. So what is nice here, which I will not have the time to develop, is that the geometry is easy to draw, and in physical terms it bridges the gap between the very big and the very small. The global space-time continuum and the smallest entities of cyclic oscillating behavior. It is the intention of this little net that you saw here. It can be interpreted as the sequence of seasons to represent a quantum oscillator with only partial observation possible, and which is at the same time generator of the global space-time. I insisted already on Petri's position that his model is actually a continuous and not a discrete one. Well, it can be given a topology in the sense that subnets that are bordered by places are open, subnets that are bordered by transition are closed, very much like intervals on the real line, and that it is not true that the fact of being in a place is a discrete statement. It corresponds to a predicate that holds true, like it holds true for an object to be in some spatial or temporal interval. And here again, to show how much of the scientific and philosophical discussions of the 20th century actually have their reflection here. This is taken from a work by Rudolf Carnap, who proposed an axiomatic characterization of modern physics only in terms of relations, and where it says up here, a space is a class of points in space-time that are pairwise simultaneous and that share at least one point with any line in the world. So that means that any transversal cut that you can place across all space lines correspond to a space. Well, so just to give a small list of the connections of ideas. Concurrency is a phenomenon that is intrinsic in modern physics and therefore cannot be ignored in the physical world. You never see what is going on at a distant place at the same time. Of course, you can wait for signals and know something about the past. and also you have an effect of concurrency in the very small. In quantum systems, uncertainty relations prevent you from having a global picture that is simultaneous and gives you all information about all states of the system. So Petri had a very ambitious program for giving an axiomatic theory of concurrency only in terms of relations. He went from binary to ternary and quaternary relations. Program is not completed here. Capture all the arsenal of tools from differential algebraic geometry, Lorentz transformation, and so forth, with which modern relativistic physics work, and in particular build a complete picture of physics, of the physical world, but with finitary means, without conceding anything on this point, without proposing an approximation, but really a complete, continuous but finitary picture. We will leave the realm of physics right now. It is in some sense the historical backdrop and probably one of the motors of the success of Petri nets and of concurrency theory. It is grounded in a very fundamental and in general principles. And I will show you some aspects of the application of techniques that use Petri nets in engineering contexts, in particular telecommunication, and sketch a little bit what we experience right now in biology. So, for those who are familiar with Petri net techniques, you will find again invariant calculus and unfoldings. I will sketch them as well as I can. Okay, you've already seen the token game. Right now, let us look at a slightly bigger example and just formalize a little bit more. A Petri net is a bipartite graph of places and transitions, and with a flow relation that connects them. And to this, add a global state that is given by a marking that associates numbers of tokens to the different places. So right here, we have at most one token in every place, and many places are empty. If you've taken some computer science class, you may see a mutex algorithm here, but this is only for the initiated. So what can you do with this? Well, you can do linear algebra. If you want to understand what the behavior of this system does, what properties it satisfies, which is important for you if you're designing a system using it. Well, you can code the structure of this graph in an incidence matrix that has zeros when there's no connection between a place and the transition, -1 if the arc consumes something. So here from P1 to T1, I consume a token. If a token is produced from T1 to P2, right here, there is a +1, and so forth. A nice...
and what is 10 here?
Sorry?
What is 10 here? Is a misprint.
Oh,
Is
that's
it
a
misprint?
Sorry.
Misprint, yes.
Shame on my head, because I copied this from another set of slides, and I must have missed it already in the previous one.
Okay.
Thanks. It's nice to see that you're actually paying attention. It's really good. Thank you. What do you do with this matrix? Well, you set it up in this easy way, and well, this matrix tells you everything that the system does to a distribution of tokens on the net. And in fact, what is true is the following: for any collection of vectors in the dimension of the number of places. Any weight vector on the places. If you have an action T, a firing of transition that transforms one marking into another, then this then the equality on the right hand side is satisfied. The difference between the resulting products is exactly given by the product of the weight on the transition with your weight factor x. And now this is interesting because this means that some vectors x will have no change at all under a transition. And if this is true for all transitions, well, this means that this weight vector is an invariant of the system. It's some property of the net that never changes under the evolution of the system, and it's called place invariant because we're based on places. And yes, what does this mean? If you do the exercise, well, it takes a little longer. I will do it here. If you complete the exercise and compute the place invariance for this net here, it so happens that it corresponds to overlapping subnets. And what happens is you have one place invariant here, symmetric one on the right hand side, T5, T6, T4, and then one in the middle that comprises exactly this square with a cross in it. And if you spell out the invariance equation with the initial marking, you see that these equalities hold, and the marking on P1 plus that on P2 plus that on P3 has always the same value. In other words, the token here only runs in cycles. It's never multiplied, and it never disappears. You can tell me, well, I can see that. It's a little less trivial to see this in the middle here, but we have also the same kind of property which is expressed down here. Why can this be important? Well, this can be exactly what you expect from your system. And in the classical application, mutual exclusion, this is what you want. You want this to be a guard that ensures that either this process here enters a critical section or the other, but never both at the same time. So you've shown this by doing some linear algebra. You didn't even have to explore all the possible states. You don't even know them now. You've taken a graph, translated it into a matrix, and solving some equations gives you the desired result. The questions?
Yeah. It seems to me, from the picture, that there can be a situation when the black dots are located, say, in P1 and in P3 simultaneously.
I don't think so.
But why?
Well, I didn't prepare the slides, so you just have to follow me here. You can move
here,
here, and then you have tokens on P2, P4. Firing of T2 empties those places and puts a token here. And that will be the only token in the left-hand part of the system. This has gone. In order to fire this transition, you have to empty this place first.
So there is no conservation of tokens. A firing may lead to two tokens becoming one and then one becoming two.
Yeah.
Right?
Well, it's a little bit like in chemistry. The tokens that come out have a different meaning from those that come in. So if you join hydrogen and oxygen, you get water. And of course, then the molecule count is not the same anymore.
Mm-hmm.
Think of it in this way.
Okay, thanks.
Okay, you can grow the numbers and markings and systems, and for instance model a production system very schematically, but still you may want to ensure the same kind of properties. This can be seen as a view of a car factory. You have some set of prefabricated kits, whatever, that need to be processed by some robots and machines. So every such item needs to be handled by one robot and by one machine. They have to match, and when they match, the corresponding transitions fire. And right here, the robot will be released, the machine will be engaged, and here the machine is freed, and another robot takes the finished item and processes it further. If you look at this with the eyes that you had on the previous example, you will see that there are again invariants. There's one for the machines. That tells you that the number of machines is always the same, only that sometimes some are active and the others are waiting. And for the robots, even if the net is more complicated for the robots, the same holds true. If you add these, and this robot together, the sum will always be R, the one that you started with. And this will be the last slide where we talk about these things. There's a huge literature in automatic control with Petri nets, where Petri nets are used as models of plants, factories, and you use them to identify the points where you should intervene to prevent something from happening or to force something to happen, so that your factory stays in the set of good states. This is something like automatic control in 2 sentences. It's not much meaningful, but I hope it gives you a slight idea of what's going on. Okay, we talked about P invariance. The dual is also possible if you take the matrix, the incidence matrix, and transpose it. You can also solve the corresponding zero equation, and the solutions for that are called T invariants. And these T invariants can correspond to sequences of transition firings that reproduce the initial state. So for this example net here, you can compute the T invariance, and you find that it corresponds to 2 subnets that you have on the right. The original net is the 2 of them fused over some places and transitions. And if you are in a position to fire any of those as many times as you like, you will always retrieve the same markings again and again and again, as long as you don't branch away. So we can do the same analysis, T invariance, P invariance for the same kind of net. If we do this for T invariance here, then the decomposition tells us which are the behaviors that reproduce the state, that iterate on the same state, that are typical processes for the system, for a factory that would be exactly interesting. And it can give us hints, I'm very careful here, can give us hints about the liveness of the system, whether the system can always continue or get blocked at some points. I'm not saying that you only have to look at T invariance, it's not true. But you have a first idea for this. On the other hand, the P invariance that we have in the mutex example, you can compute them in this example as well. It gives you a decomposition that is not quite the same. If you're familiar with finite automata, these Petri nets are in some sense representations of finite automata. And like we've seen, these invariants are able to express properties that all reachable states must always satisfy. For instance, here, in each of these invariants, there will always be exactly one token. On different places, but never more, never less. If you're able to cover your entire system by such invariants, that means that it must be bounded. It means there must be a bound of the number of tokens that can be in any place. It's not possible otherwise. You may be able to decompose your system in such a way that you analyze smaller subsystems and understand them better. And yes, once again, you may imagine that for control, supervision of plants, etc., these invariants are very handy. I'll come to telecommunications in a moment. Just let me remind you here that the subject is Petri nets and concurrency. And right here we've forgotten a little bit about concurrency. We've done some global analysis of the entire system at once. Well, there are domains where you cannot really do this. Telecommunications is one of these. So these slides don't require you to know anything about telecommunication engineering, I reassure you. The problem is that telecommunication networks are very big and very fast, and things happen all the time. If you have an optical network, for instance, then information must be sent through lasers over a glass fiber, and the glass may break, the laser may break, the reception may fail, and so forth. And if that happens, you don't see it directly. You want to infer that such a problem has occurred from some other trace. And this is what you call fault diagnosis. It became very crucial some 10 or 15 years ago. So these pictures are actually taken from an actual research project with France Telecom. So this is the canonical symbolic representation of an optical leak, where things can go wrong. Loss of signal is one of the typical problems if the laser on the other end of the fiber goes down. TF is a potential risk, total failure, after non-reception of a signal. Now, the problem is that networks, even when they are localized, are very big, and even this is very schematic. This is the inscriptions are not legible. These are 4 sites around Paris in which major switches are located, and in each site you have a hierarchy of interconnected elements that react to one another and depend on one another very heavily. And they're of course connected among themselves by optical fibers. Now, what happens if something goes wrong? Well, if something goes wrong, it doesn't stay confined in one place. Okay? Let's say we have a total failure down here in Gentilly. This will bother the colleague in Montrouge, who will create bother all through the side of Montrouge, and then another failure for the sender at Montrouge will occur, which will bother Gentilly, and will escalate through the digital hierarchy and bother high placed elements in other sites. This is nice, we understand it. But the supervisor does not see any of the arcs. The supervisor only sees the dots. And now the problem is telecommunication networks are fast. So all these dots appear virtually simultaneously for any reasonable observer. So it was not possible to continue like it was still in the 90s, to have a human supervisor looking at screens with red and green lights popping up when things were reported, because there were too many of these signals. They came too fast. So you need a computer algorithm that is able to do the correlation and the deduction of faults for you, and you have to feed this algorithm by mathematical models. So this is where concurrency comes in, and this is where veterans will come in. So what happens here? You have remote sites from which sensors will inform a supervisor situated somewhere in the middle of the network. And the supervisor will see the streams of alarms coming in. Well, this is very reminiscent of physical space-time. You have sites that are at a certain geographic distance from one another, and they are not able to give a unique and uniform timestamp to all their observations. Because whatever happens here happens at the same speed with which they can transmit their alarms. So the supervisor here, seeing something happening there, will not be able to tell which came first. So, what can you do? Well, you try to remember what you know about concurrency, and that there are actually models that allow you to capture it. And for these models to be used, you need to do some abstractions. This is how the engineers had represented the procedures that were triggered when a fault occurred. That was much too much information. So we had to do away with a lot of this. Basically reduce the kind of information to the type. Well, we have a collection of preconditions that trigger some event, and this event triggers some alarm, or maybe not. Well, the alarm is what we represent in a Petri net as just a name, just an identifier on some transition. All the rest was irrelevant for the problem, or irrelevant for the question of fault propagation. Sorry. But all we retained was the structure on the right, which is of course a little Petri net that you can compose with others. Well, remember this the picture of the global system and its size. What is the advantage of the Petri net on the right-hand side compared to an equivalent representation of the same process that's on the right? Well, the inscriptions are missing. The intention is to have a transition A here, here, here. Whenever you go on this diagonal, C down here, and B in this direction, or this or that. So any process that can occur here, first A, then B, then C, or first A, then C, then B, etc. You can find it on the right-hand side, and the big dots correspond to the global states of this. Well, the first problem is that without inscription, or even with inscription, you don't understand much on the right-hand side. The second, even bigger problem is that I could still draw this because there were just 3 transitions. What if there are 100? 100 copies of this might still fit. 2 to the 100 states. It's hopeless. I cannot draw them. I don't want to draw them. I don't want to block memory space and so forth. So we are motivated to keep this nice concurrent compositional representation as long as possible and do our analysis with it, because we save time and we understand things better. And for this, Petri nets are very handy once again. We set up models that contain only transitions for fault propagations. So everything else that happened in the network was not modeled at all, only the fact that something went from OK to KO, or went back by repair to it. And then, of course, the connection between different components were explicited by Petri net arcs. And then, what is handy with Petri nets is that you can use them to model the system, and you can model the observation also as a Petri net. The observation, what was that? Well, it's the chronicle of all the alarms that come into the supervisor. And to make things simple, suppose that this is just a sequence of labels beta, alpha, rho, beta, alpha. We just put them in the sequence, and we turned it into a Petri net. Now, what we want to do is use our model to extract the possible behaviors that are compatible with this observation. What can the Petri net do that would result in this sequence of labels? And we don't have to explore all the sequences for that. We can do smarter. First of all, I said that we would like to keep concurrency as much as possible. Well, exactly. We don't draw all the sequences. We don't interleave all the possible combinations of transitions. But we draw a partially ordered structure of this sort, but just keeping track of possible occurrences. This is the net in its initial state. Copy the initial state, and then for every transition, for every occurrence that is possible, we glue a copy of the transition with its environment to the prefix that we already have. And in this way, we get a structure that grows with time, of course, and that contains a representation of possible behaviors of the system. So now we wanted to filter those behaviors that are compatible with the observation. So do we have to look them up in here? No. We can do smarter than that, because Petri nets allow us to synchronize, to add more constraints on the same transition. So remember, this is the picture that you get if you have just the model of the plant. Now add the model of the observation and fuse those transitions that have the same name. So take this beta and marry it with the betas from the net. The labels are not in here. You have some here. But alphas come in over here, and rows occur in different positions and so forth. This gives you a slightly messier unfolding structure. But yeah, why is it so messy? It is messy only because we have these additional spurious artificial places from here. They were only there because we had drawn this observation as a Petri net. For our inference, we don't need those places anymore. And if we throw them out, we have a nice structure on the right that contains all the information necessary, all the possible executions of the system that are allowed by this. And then you have to push a little further, and you see that, well, the parts in white are not possible because they explain only part of this here and do not go far enough down. In the blue parts, you have the right explanations, but you have to make a choice between the two instances of row, because up to here you only have one row, and so forth. So you still have to narrow down, you still have to do inference, but you do it on smaller and smaller data sets. And this was possible because of the power and the nice surgery that you can do with Petri nets. Okay, I think I have another 10 minutes or so. Or what's the usual schedule? Okay, so we had talked about physics. We've talked about engineering, and I already admit that on the last slide I will tell you that there's so many things that I will never talk about and not have the time to talk about, not even workflows, so I apologize to Irina, but she would be in a better position than me to explain that. So now, biology was not traditionally a field that was attracted by to Petri nets, and it's not a field where you would expect concurrency, because living organisms are not usually spread over distances that create relativistic effects. And still, we have an increasing need for not just formal models to explain biological phenomena, but also to deal with huge networks of manufacturers acting independently of one another. So this picture shows why biologists of today are increasingly motivated to use formal models because they need to understand which behaviors emerge from complexes of regulation networks, and they need to test their understanding of the system by putting their models to a test and improving the models after the test and so forth. So some nice mathematical language is really what is needed here. And well, to pick one topic, the one of gene regulatory networks. So these are formal abstractions, or pre-abstractions in some ways, of the processes that determine how genes actually affect the life of the organism that they're supposed to determine. Remember that genes are at best something like computer programs, code that you write, and then on runtime many things can happen, and interactions with other systems can influence the result and so forth. It's a very crude analogy, I apologize. So what happens is that you have a great number of substances involved whose quantities are important to see which features will be suppressed, which features will be developed by the organism. And when these understandings were collected, starting in the 90s, if I am not mistaken, the conventional way was to do away with the quantitative information and draw qualitative diagrams like these, with just pluses and minuses between on the arcs between two substances, meaning that the presence of A favors an increased production of C, or the presence of C diminishes the production of E, and so forth. Which is nice if you look at 2 or 3 such substances, but if you ask me what is the precise impact of A on D, it is not possible to say in this, because you lose qualitative information, and the qualitative information does not take you far enough here. So what is currently happening is the observation that such a positive negative modeling is nicely abstract, but probably too abstract. You see here the number of components that you can have. This example is ridiculous compared to the networks that biologists today have to look at, or not even look at. They're happy if they can store it somewhere on the computer. Right? Now, what if we do this in a slightly richer way? Instead of just stating that there is a substance A, let's say that the substance can be present in two or more levels. It can be absent, present, strongly present, and so forth. And then every substance becomes a little finite state automaton that moves from one state to another according to influences from outside. And we can keep the memory of what happened to the substance in the system. So let's suppose we start in something like this, and some action lambda 1 occurs, then most substances are not concerned, but one changes state, and then moving on, you keep track of what has happened in other parts of the system, and you can start asking questions once you've started this. Is a state reachable where the substance E is actually present? And here we're talking about things that can be important for the life of the organism or dangerous for the life of the organism. So these are not purely academic questions, right? So there's some need behind this. And I cannot say that we have today really the algorithms to solve this. There are many algorithms dealing with these systems in an approximative way. So you find some behaviors, maybe not all of them. Sometimes you get too pessimistic and you see dangers everywhere, even if such a process is not even possible. And what we are arguing and what we are starting to do in Paris is to say that, well, if you use Petri nets, you can be exact. You can, if you're smart enough, you will be able to have the exact information of the properties of your network. And not only this. Remember that one of the first slides I showed you, we're talking about chemistry here, and chemistry and Petri nets are close friends. It's also been observed by biologists and computer scientists. This is taken from a tutorial by the group of Monika Heiner in Cottbus, where an enzymatic reaction, where some substance is present in blue, an enzyme activates a reaction that produces some output substance, some product from this substance. And this is really what you can say with a Petri net transition, with a slight extension from what we said, because you want to express the enzyme in such a way that it is just present but does not consumed itself in the reaction, but if ever you stumble upon contextual nets, these extensions exist and they're increasingly well understood. And also, using Petri nets gives you some sort of a collection of Lego bricks that you can put together to create new meaning. You can have this enzymatic reaction with some gene expression that provides your enzyme, for instance, or that removes the enzyme and therefore stops the reaction from continuing, and you can integrate the elements in larger networks, moving upward to do greater abstraction. And just to show a little bit what we have achieved as a first application, we are looking at the problem of computing attractors in such regulatory networks. What are attractors? You may know that, for instance, the cells of the human body all have the same genetic code, but not all of them have the same shape or function or role in the body. And in some circumstances, for instance, if you're hurt, cells can change their role and differentiate into different roles. This is how skin gets repaired after you get hurt, for instance. And if you have a graphical representation of all the states that the organism can have, that the cell can have, well, this corresponds to a terminal strongly connected component of that graph, where you always turn around. And computing these attractors, of course, tells you a lot about the possibilities of some organism. So it sounds like wonderful news, but computing them is so hard that it doesn't mean that we have biology already on the computer. No, this is not the case. For every case where we have this, we know that there is some particular stable state of a cell, for instance, after differentiation or de-differentiation. What are the mutations that are reachable from the current state? And from that you want to go further, because behind biology there is medicine. If you know what kind of mutation, what kind of role change is possible, maybe you want to do something about it. Maybe you want to block it, or you want to encourage it. You want maybe to encourage the regenerative power of an organism, or you want to prevent cancer, if you can. So it makes a lot of sense, I think, to go and model these networks and propose algorithms for precise predictions and control of these biological processes. We've done this in a very small and sketchy way. So if you represent a small regulatory network by this small Petri net, well, if you look for attractors in the natural, immediate way, you compute the state graph, what are the markings that you can reach, and then you will find that there are two attractors here. One is up here. Once the system ends up here, it will never leave that state, and the other is rotating at the bottom. Okay, if you have this graph, you can find it by graph traversal algorithms and so forth. Just remember that you're dealing with something of the size of 2 to the power of, and then you have something like 10,000 in the exponent. It's pretty hopeless. Whereas, if you compute the unfolding, the same beast that we used for the fault diagnosis in Telecom, well, the same system has a structure in which you can see not only all the states, but even all the behaviors. What we can do here is identify the processes that are possible to iterate on the system, which is exactly what attractors do. they return to the same state and never leave a certain class of states. And from the unfolding procedure, we had immediately two attractors with their internal dynamics. Well, there's not much dynamics in the second one, of course, but this one came out as the direct result of the Petri construction, with the information that after this event you can start again. This is very recent work. Exploitation of this is still to be done, but there's potential, and there's actually a wealth of real important questions that are waiting for us. So, just some leads of what Petri nets could be able to do in biology: accelerate the search of attractors and find cut sets. Cut sets meaning sets of factors or events that are necessary in order to reach a certain part of the system. So that means identifying what is the factor that influences your health in a good or a bad fashion, or what would be the drug that helps against this mutation, etc., etc., etc. So if you know cut sets, you know a lot of how you can influence a biological network. So you have a lot of questions. We are trying to get a project on cell reprogramming, which basically puts the two together, understand what are the possible attractors and how do you move from one to the other to reprogram a cell. And I mentioned, for instance, the work by Monika Heimer and her colleagues, using invariance, using compositionality in analyzing regulatory networks. Let's not forget that synthetic biologists are starting to build up genetic circuits from small elements, very much in the same way that we are used to gluing Petri nets together. So if we know something how to verify and test properties from Lego bricks to their compositions and so forth, they'll be happy to use it. Of course, control, monitoring, and so forth. I would just have to stop here because the list might get too long. Okay. Thank you very much for being with me until this point. Let me just resume the things that I did say today. I hope I convinced you that PetriNet as a model and the phenomenon of concurrency are both meaningful in a strong sense. They correspond to something real in physics, in engineering, of course in chemistry, and increasingly in biology. It's not just paperwork. The concurrency is an inherent property of systems. It's also intuitive. Remember that sometimes representing concurrency as such tells you more of the system than gluing everything together. And contrary to common prejudice, you can actually use concurrency to help you save time in analysis. What I didn't say is that there's a lot more of models to be looked at, a lot more of analysis methods, a lot more applications, and these are only those ones that I thought of when writing these slides, and I certainly forgot things. I'm indebted to a number of references that I will show you on the next slides, and what I have to say to you is a big thanks for inviting me and for following me here. Thank you.
Probably I will have a question, which I had from the
beginning, but probably it's more appropriate for the end of the talk, which is when you made this remark that Petri himself said that these are finitary models of continuous
Yes.
subjects. So could you say a few words on the temporal dynamics? I mean,
So the temporal dynamics.
yes. I understand that there are combinatorial rules of firings and of counting tokens, but how is this mapped on the timeline?
Yeah, this is actually when Petri was alive. This was a recurrent subject of debate when he came to Hamburg University, because he was strictly opposed to any attempt of including real time in the models. There's a big literature on Petri nets where the fact that transitions take time is explicitly modeled, or where transitions have temporal constraints, and so you have semantics that you best express as timed automata with durations and time invariance and so forth. The temporal progression in the very canonical Petri-like interpretation would have to be the inclusion in the net of some explicit oscillator process that corresponds to the cesium in an automatic clock, for instance, that you have as one active process, and that sets the pace, and the timeline, in quotation marks, arises from the fact that particular clock ticks synchronize with particular other events. So it could be complicated to do this, but let's say it can be done.
I see. Good. Other questions? And probably one more thing is whether this is, so to say, a language to describe concurrent systems, but probably not the only one. Probably, I mean, there is a paradigm of finite automata. So, can these different paradigms be translated into one another? I mean, an example that I'm having in mind is that in theory of computing there are several fundamental models of computation which are equivalent, and that's I mean that's a theorem. You can prove that you can express Turing machine in terms of Markov algorithms, for example. Now here this is not the only approach to concurrency which is conceivable.
The pitfall in questions like this is in the notion of equivalence. Because as you said, for models of computation you had a very predefined notion of equivalence, and the same also holds true for models of concurrent systems. You can describe any concurrent system also by a transition system, which is an automata that may not be finite, and then you have other descriptions, more semantical, like process algebras and so forth. And let me put it this way: for every translation, you can provide a good justification in stating what exactly is the equivalence relation that is satisfied by the two points of the translation. Just to cite one example, I mentioned this decomposition into P invariance of a system that can be seen as finite automata, each one in itself. So basically you end up representing a complex Petri net as a collection of automata that synchronize at times. Add time to this, and this gets more complicated. You have time automata that synchronize and so forth. And we ended up showing that the translation that we give is the right one, but in terms of an equivalence relation that takes into account not only the interleaved behaviors, but also some other property of events, particularly the locality. What is the component that the event belongs to? Is that respected by the system that we translate it into? So what happens there is not just technical. I mean, of course, I want to defend ourselves. I don't want to say that we were cheating. We were not cheating because it's an actual information being realized in a sequential local way, or being realized in a distributed way over remote sites is not the same thing. And if you look at equivalence purely from a temporal way, then interleaving and concurrency make no difference. If you take space into account, the picture is entirely different. This is a very partial answer, but I would certainly think in these directions.
Thank you. Well, let's take a speaker again.
I could advertise for students that there will be one more talk by Professor Stefan Haar next Monday at our laboratory seminar. You can find information at our webpage, and then there will be more special topics. Also, those of you who are interested in Petri nets and different aspects are welcome to our laboratory.
And one last advertisement is that, as I said last week, this seminar is supposed to be held twice a month, normally at second and fourth Thursdays of each month. And the next one will be on 9th of October. And the speaker will be Geoffrey Decouer, who will be explaining what multifractality, what every computer scientist should know about multifractality.
At what October?
9th.
So in 3 weeks, right?
Yes.
Я написал какие другие даты. А я совершенно не имею в виду вашу. Я просто не имею.
Она пришла вместе.
Я думал, вы пустили вместе с ручкой.
Нет.
Кто-то мне просто...
Коллеги, а белая такая ручка с зеленым, она чья?
Ну, передали сам. Я вам
Вот, вот, я просто когда я подумал, что это, ну как бы это приближается 25 тысяч лет, я позавчера
да, я просто не заметил.
как бы,
Сейчас пришло. Он там согласен.
ну вам это удобно?
Абсолютно.
Да. В прошлый раз не было слайдов, но запись есть, сегодня будет написано, а в этот раз слайды образовали абстракту, а YouTube
Здесь февраля, да?
А смотря что они спрашивают.
То есть я как бы могу быть...
Получается, моды.
There's a way to do that for maybe because this would remember where it comes from. We have a system that is
Нет, я не про это, я про то, что вероятность предметов подавать не обязательно. А, хорошо. Работает. Если ВКР можно знать, как работать,
Ну, ВКР можно сделать для галочки, а можно сделать такую работу, потом